today our speaker is Anton Melnikov from the Fraunhofer Institute for Photonic Microsystems, and he's a big specialist in acoustics and metamaterial in acoustic region, as far as I know. And I think he's working already with some of our colleagues who are here already. So we're looking today to for his talk about acoustic metamaterials. And if you're having a question, I think you can raise your hand in the Zoom meeting, and I will interrupt the speaker so that you can ask your question. So with that, I think we can start. And Anton, welcome to your talk.
Thank you for this kind introduction, Mikhail. And at first, I want to thank you, Mikhail and Alexey, for inviting me to this seminar. And I'm quite excited to have a talk today. And the topic of my talk is about acoustic metamaterials, and especially about noise control, Willis coupling, and anomalous reflection. And I will try today to convince you guys to work with acoustics and acoustic metamaterials. So, and first I want to show my outline. I will speak about acoustic waves in general and show you some general facts about acoustics and hearing, since I think most of you are working with electrodynamical waves, and therefore probably you will be also interested in some general facts about the acoustics. And then I will go further to concepts for noise mitigation and show some work from our sides, where also Jan Pojanka has contributed to. He's today also a listener. And the third point of my talk will be about Willis coupling and acoustics of acoustic scatterers. And I will explain what is Willis coupling and how we can use it. And the last point will be anomalous reflection and how we can design materials which would provide anomalous reflection in acoustics. Okay, but let us start with the introduction. And at first, I would like to say why acoustics is important. And probably someone could say acoustics, yes, you have here acoustics, there acoustics, but it's not so important at all. But if you really look around and you would just consider the speech, which is transferred through acoustic waves, it is very important measure for us of our communication. And all the branch of communication acoustics is quite important for us. And even today, I'm using the microphone and loudspeakers, or you are using loudspeakers, and it is only possible due to the acoustics. And there are a couple of electroacoustic devices and so on. There is also a huge branch of psychoacoustics. And if you go around in the industry, or maybe also just in the big cities, you have also issues with noise, and you have also issues with noise and vibration in the industrial applications and the factories and so on. So you have also to provide some noise control there. And you have also acoustics in the plane or in the car, so you have cabin noise. Then if you go to other frequencies, because now I have spoken about audible frequencies, and if you look around and go to ultrasound, for example, you have many ultrasonic devices which are using all the day long. And for example, like in your car, you have a parking sensors, and usually it's a ultrasonic device which is also acoustics. And in your mobile phone, you have some MEMS and MOEMS things, and usually you use acoustic wave for your microprocessors and so on. And you have, if you look at large scales, you have seismic waves like earthquakes and sea waves. You have also music, and if you look around, acoustics is really everywhere. So I'm quite excited to have the possibility to speak today about acoustics in your group. And I want also to present some general facts about hearing. Just take it like an entertainment, because it's not really linked to acoustical metamaterials, but maybe it's just interesting to know. And of course, we are using our ears for hearing, and if you have some acoustic waves around your head, so you have to transfer them through this small canal to the eardrum, and already here in the entrance you have an impedance matching problem, and where you have the pinna which can help for it, and then you have the eardrum where you have surface fluid structure interface, and you have again an impedance matching problem. And then if you somehow managed it, and nature has really managed it quite good, then you have to transfer the wave through the ossicles to the inner ear. And these ossicles, these are very, very tiny bones, which are the smallest bones in our body. And probably also this is the most complicated mechanical part of our body, which is very interesting. And the nature have managed it to create like a microphone or a sensor, which is very broadband and also very sensitive. Owing to that, we can perceive sounds between 20 Hertz and 20 kilohertz. And also, we can perceive sounds in 6 order of magnitude. So we start at 0 decibel, and it's like the threshold of audibility. And when you reach to 120 decibel, you would experience some pain, and in between you can really sense 6 order of magnitudes. And here at the picture, these are phones, but doesn't matter too much. And then our ears are also providing us with frequency analyzing. And even some humans have absolute pitch. So they can tell you if they hear a sound, they know exactly which frequency that sound has, or better said, which note it is. And usually these are musicians, but it's really an interesting property. And also, which is very important in hearing, this is a direction recognition. Thanks to the fact that we have 2 ears, we can recognize the direction where the sound comes from, and which is very interesting. It's like a born-in future. I have seen it by my newborn daughter when she was just a couple of hours old. When there was a sound, she was really a baby, very, very small. And then when there was a sound in the room, she knew where it came from. So she just turned her head in the direction. And it's really impressive that you can do such things just when you are the first hour in the world. Because if you want to do it with some microphones and on a digital way, it's quite complicated task. And thanks to this directivity recognition, you can also use selective listening. So if you are in a party, for example, and you want to talk to your neighbor in a loud environment, you can still understand him, because thanks to psychoacoustics, you can increase or amplify in your head the sound up to 10 decibel. So, and what is also interesting is the hearing range of us. When we are small children, the hearing range is 20 Hertz to 20 kilohertz, as I mentioned previously. But when we got older, then the upper limit decreases. And usually in our in our age, like today, the threshold is 16 kilohertz. But here I have a diagram. This is just from Wikipedia, but I really like it, which compares different animals. And here you see the hearing range of human. And if we compare it to other animals, it's quite not bad, I would say. Of course, there are some other animals, like, for example, the cow, which have a broader hearing range, but there are also other animals like chicken, which have very small one. But just as a side information. Okay, but let us continue now with real technical stuff, with acoustic waves. And acoustic waves, it is energy which propagates through a medium. And usually when you speak about acoustic waves, you mention, or you mean gases in liquids, and you mean pressure waves. But you can also speak from acoustic waves in solids, or sometimes guys say to it elastic waves. And usually these are compression or shear waves. But we will not consider this kind of waves in the following slides. We will focus on waves in gases and liquids. And there is a linear acoustic wave equation which is here, and it's determined by the speed of sound. And the pressure in acoustics is a scalar potential, which is a difference to electrodynamics. And usually the acoustic media are specified using the speed of sound and the density. And the common media which you usually use for acoustics is air or water for underwater acoustics. And air has a speed of sound of 343 meters per second and a density of 1.2 kilogram per meter cubed. And in water, it's 4.5 larger as in the air, the speed of sound, and the density is, which is not surprising, 1000 kilogram per meter cubed. Okay, which are further differences to electromagnetic waves? Acoustic waves are always linked to movement in media. You have really some physical oscillations of particles. And also for this reason, of course, you need a medium to have acoustic waves, because it's not possible for the acoustic wave to propagate in vacuum, of course. And which is also interesting that the acoustic waves are usually longitudinal in nature. It means that the oscillation of particles is also in the propagation direction. But this fact accepts the case of shear waves, which would be also transversal, which is comparable to electrodynamic waves from the point of view of the direction. And which is also interesting is the speed of sound increase in acoustic waves, because usually you have the slowest waves in gases, and if you go to more dense matter like fluids, the speed of sound increase and you have the fastest or the largest speed of sound in solids, and this sequence is different for electromagnetic waves. Okay. And the next slide, I want to give some motivation about why we want to study acoustic metamaterials, or why it would make sense to do it. And of course, there are many possible applications for acoustic metamaterials. As I mentioned before, you have many different branches of acoustics, and therefore you can use, of course, acoustic metamaterials for noise control, for impedance matching, almost at every kind of devices, and also for beam steering. And of course, this opens a great potential for new devices. And which is also a great news is that many metamaterial concepts or have been already studied in electromagnetics. And of course, you can, since you have many similarities to the waves in electrodynamics, so you can transfer many of that concepts to acoustics. And which is also a very good point is that the experimental setups in the acoustics are much more simple as in the electrodynamics. And usually you need some loudspeakers and microphones to create and detect sound. You don't need any special materials, because usually you use air or water and you need probably some boundaries and so on, but you can use the materials like steel, aluminum, or even polymers to create such boundaries. And acoustic absorbing foam is very cheap, and you can get it in from almost every store. And it is very simple to realize waveguides in 1 dimension or 2 dimensions, and which is also very interesting that the size of the unit cells of acoustic metamaterials is mostly in centimeter range. Of course, not always, but the audible range, like probably in between 100 and 2000 hertz, or even 3000 or 5000. Usually it's not too complicated to touch these things. And I have here in my hand 2 different metaatoms, like the unit cell of acoustic metamaterial, and this is like a Helmholtz resonator, a C-shape, or a pipe with the slit. You can see it here, and this one is resonant at 1.5 kilohertz, and this one is just a bigger pipe with a slit. Here you can see the slit, and this is a resonant at 800 hertz. Therefore, you see it is very easy to manufacture them. You can use some things in your lab just to create such structures, or you can 3D print them or use mechanical machining for it.
Yeah, there is actually a question, is it 3D printed?
This one is really, both of them are 3D printed.
Okay, is it some special plastic or just the usual ABS plastic?
It was the usual PLA plastic.
PLA.
Of course, it has some issues because you have surface impedance and so on, and you have some losses, but even with the losses of these plastics, it's possible to get quite good results.
Okay, thank you.
Okay, so that was my last slide for the introductory part, and I would go further to the second part of my talk on concepts for noise mitigation. And at first, I would like to say some words about the requirements which you usually have for noise control. And of course, if you design some noise control things or noise barriers, you would like to have broadband noise mitigation and high insertion loss. But if we are honest to ourselves, these 2 points are perfectly handled by conventional noise barriers like porous materials or Maslow and so on. So usually if you say you would like to have these 2 points, so it is not really necessary to use acoustic metamaterials. But if you consider other requirements, like for example, sub wavelengths of your barrier or air permeability or lightweight design, this would be points which can be realized with acoustic metamaterials pretty well. So, and I have here at the next slide some examples from other groups. This on the left side is a photonic crystal, sonic crystal created by Alford, and he had used a C-shaped resonator, and you see here on the picture that as you know it, at some frequencies the waves can propagate through this sonic crystals, and at some frequencies not. And on that side you see the K vector of the infinite sonic crystal, and which shows some band gaps here and here and here. And when you create using this sonic crystal some finite structures, you can create stop bands here and here. And you can of course use this to create noise barriers, which would be also quite efficient. And or there are also other approaches, and here is another example which is really a favorite of mine. It's a paper written by Claes and his colleagues, and he had used such a small piece which was 3D printed. It is a resonator, and he arranged it on a plate, and the plate is not air permeable. These are like small cells, and in every of the cells you have such a resonator which sits inside. And this structure, if you consider the shear waves, you would have a band gap in somewhere here in between 1000 and 1.2 kilohertz. And if you then do numerical simulations and experimental investigation of transmission loss, you see that you can create transmission loss in the area of or in the region of these band gaps. But what is interesting is that this kind of metamaterial, I don't think that there are analogies in electrodynamics, since you are using here the shear waves propagation. And you know, if you have such a plate and from one side you have acoustic pressure, and usually in solids you have two kinds of waves: transversal waves, where you have the oscillation and wave propagation in this direction, for example, and you have the shear waves where the oscillations are orthogonal to the plate, and the propagation would be also in this direction or in this direction. But you can only excite shear waves with air pressure if you have such structures. And also only shear waves can radiate sound, and therefore you can create, using the shear wave band gaps, stop bands in the air domain. Okay, but at the end, if you again, consider this photonic crystal. Of course, it's air permeable and lightweight, but it is not sub-wavelengths, because you need such a bulk of material to get enough unit cell to come in the direction of infinitely large sonic crystal. And if you consider this kind of design, yes, it is sub-wavelengths, but it is not air permeable. And it would be very great to have designs which are sub-wavelengths, air permeable, and lightweight. And therefore, we made another proposal trying to combine these three properties, and we used a very, very simple C-shaped geometry, which can be arranged in a single layer metagrating. And at distinct frequency, it would create also a stop band. And it was designed to create a stop band around 1.5 kilohertz. You can see it here. And at that frequency, the metagrating has a thickness of 0.17 times the wavelengths, which is below the borderline case of 0.25 times the wavelengths, where the porous materials stop to be efficient. And another nice feature of such a simple C-shaped resonator is that you can model it analytically. And here you see the expression for the impedance of this resonator. But now this is just a grating without any, it is not a device. And we then expanded this grating to a real three-dimensional design of noise capsule. And you see here the design of it. And it is intended that you have a sound source inside. This is like a cage. And then you have three walls consisting of this metagrating and three walls consisting of absorbing walls. And why you need it? Of course, one can think that you could also just place only the metagratings around. But the problem is that the metagrating itself is it provides only reflection and not absorption. And you need also some places where you can dissipate the energy. Therefore, you need some absorbing walls inside. And it was designed to have a peak at 1.5 kilohertz. And now here at the diagram, you see the experimental and simulation results. And the blue curve is the experiment. And you see that in the experiment, we see this designed peak. And this purple curve is the simulation. And also in the simulation, you can see this design peak. And we also use this impedance model, the simple model, to fit the height of this transmission, but the frequency is given by the model. But of course, this impedance model is a perfect model which don't have any losses and so on. And you have to, if you see this kind of not perfectly efficient device, you have to reduce the efficiency of this impedance model, or not the efficiency, but the efficiency of the resonator in the impedance model to match this peak. But which is also interesting in that case, by the way, is that you see here a broadband attenuation region. It was not intended to be there. We only focused on this design peak, but we got this broadband attenuation, and we also got some broadband amplification here at higher frequencies and also at lower frequencies. And of course, this amplification at lower frequencies is very, very parasitic. You don't want to have it. Okay, but what is the reason for it? And to understand the reason, you need to take a look at radiated power. And when you analyze radiated power of the source and the far field radiated power, you see a very interesting effect. This light blue line is the source radiated power over the frequency. And by the way, sorry, I have forgotten to mention one thing. I will go back to this figure, and what you see in that figure is the transmission of the capsule. And the transmission in the sense that once we measured only the sound source on the plate and also did the simulation of it, and also Afterwards, we did a simulation with this capsule. And then we analyzed the pressure at a distinct region in front of this metagrating. So this transmission, what you see here, is the difference between the pressure measured in front of the sound source and the pressure measured at the same place in front of the sound source covered by the metagrating or metacapsule. Okay, and the same thing you see here, but now in a sense of the radiated power. So, and now you see again here this blue curve with the radiated power, and already in the source radiated power, you see an amplification in this lower frequency region, and it is nothing else as acoustic Purcell effect. And we were quite excited, and when we understood the source of this problem. And but if you consider this region in between 500 and 2 kilohertz, where you have the broadband attenuation, you have also the broadband attenuation here at the source, which is also good news if you want to use this for noise control. And at the end, the far field radiation, the difference in far field radiation, this deep blue curve, that's the true transmission of the noise capsule, which don't considers any directivity effects and so on. And also in this true transmission, you can see this designed peak, which is a little bit different to the peak in the pressure, but pressure is of course dependent on the place where you measure it. But you also see that this amplification at higher frequencies is not there in the far field radiated power. But of course, this parasitic amplification below 500 Hertz is an issue. Okay, but now when you have this kind of capsule, you would be also interested to apply it to some device. And we have applied to machinery noise of a drivetrain, which is intended to be used during opera performance. It's like, it is stage machinery. You use such a drivetrain to elevate stage platforms, which would be here on these 2 parts. And usually you have 2 of such drivetrains, and they then elevate a huge platform which is part of the stage. And usually if you are a listener in opera, you don't recognize such things because they are below the stage. But sometimes, if you are lucky, the actors or the directors are using them to provide some effects. They just elevate a choir and so on. And of course, if you have paid $150 for, or maybe $300 because you bought 2 tickets for you and your girlfriend or your mother, you don't want to listen to the noise of some machines. You want to listen to the singers, to the choir, to the music. And therefore, such as drivetrains have to stay below some levels. And the noise spectrum of this drivetrain was modeled using different numerical techniques. And then it was observed that there are some critical peaks at these frequencies, at these 3 frequencies, which raised the 1 kilohertz octave above the normal, this allowed limits. And for that reason, we designed a metagrating with 3 different layers, which has this kind of transmission and would be effective, not broadband, but only at the 3 critical peaks. And if you reduce the critical peaks, you can reduce the transmission, or not the transmission, the emission of the noise in the 1 kilohertz octave and stay below the limits which are allowed. And it is an example for application of metamaterials for real devices. And here, of course, I have to mention, it is a simulation. It was not possible to test it in real application. And And here, for example, the property that the acoustic metamaterial of this kind would be sub-wavelengths is very, very appreciated because you don't have any space below the stage to use huge porous layers of material. Okay. But okay, this is probably an interesting application, but noise control is not the most interesting application for metamaterials. And therefore, I want to come to the next point, which is Willis coupling of acoustic scatterers. And it is for me more exciting as noise control. And what is Willis coupling at first? Willis coupling is a kind of coupling which was named a guy with the name Willis. He has somehow invented this kind of coupling or understood it. And Willis coupling is nothing else as acoustic analogy of electromagnetic bianisotropy. And it couples potential and kinetic energy. And now one can think what is special in the coupling of potential and kinetic energy, because it's somehow everywhere, but it couples these energies in a very distinct manner. And if you express the polarizability of acoustic material, acoustic scatterers in the way that you have on the left side the monopole and the dipole moments, and on the very left, right side, you have the incident pressure and incident velocities. The Willis coupling terms, or the terms which corresponds to Willis coupling, would be in that polarizability tensor at the off diagonals, which are here in red. And they couple the incident velocity to the monopole, and the velocity, and the incident velocity is linked to kinetic energy, and monopole source is linked to potential energy. And at the same time, Willis coupling couples the pressure, the incident pressure, which is again linked to potential energy. And it is coupled now to the dipole moments, which are linked to kinetic energy. And the moments can be then used to recreate the scattered field. And why here we use only the monopole and dipole moments? Because when we have particles which are sub-wavelengths, we don't have to consider the higher moments. Therefore, we can stay with only monopole and dipole moments. And a monopole moment is a source which creates this kind of scattered field, and a dipole moment is a source which creates this kind of scattered field. And of course, you have this, if you consider two-dimensional space, it would be this, and then three-dimensional, you have this third one. But here I stay with two-dimensional to keep it more simple. Okay. And now the question is, what are the benefits of Willis coupling? If you can redirect the energy, for example, I would go for a moment back to that slide. If you, for example, have a grating and you would like to redirect the energy from incoming wave, which comes from, for example, maybe I have to use this nice tool. Okay, just imagine you have here some kind of acoustic metagrating, and your wave comes from that side. It's your wavefront, and then you would like somehow to create interesting exotic effects with maybe, for example, you want this kind of refraction for an incident wave with an angle of 90 degrees or 0 degrees, depending on the axis. And you have to somehow redirect the energy in that direction. And then you can do it using this bianisotropy or Willis coupling, because you now can redirect the energy from the incident wave to this mode or to the scattered field. And if you find a perfect combination of all these moments, you can create effects like refraction, which would be very anomalous, of course. Now I would like to delete it. Great. So, and at the next slide, I have some examples. which should again show the benefits of Willis coupling. And here it is a metagrating proposed by Li Kuan and his PRL paper. And it is a reflective metagrating. It is intended to reflect the waves with anomalous angles. And here you see this is a cylinder with a bianisotropic inclusion, and it is in front of a wall. And at this diagram, you see the transmission of an incident wave to the minus first zeroth and first Floquet mode. And the minus first Floquet mode is directed in this way, and you see that at frequency around 2.405 kilohertz, you link the whole energy to that mode. It is like an impedance matching in this direction, and which works for reflection, works also for refraction. And here it is another example. This is a paper from Craig, and he used this kind of T-shape, which is also bianisotropic, and he also verified it in an experiment that you can, for example, if you have this kind of shape, you can reflect the waves coming from that direction to the same direction, or you can transfer the waves which come from the direction to the direction. And you see here some experimental results where he showed that you can actually refract the waves in that way. Of course, now you see that it is important, and this is only possible with Willis coupling. It would be not possible with scatterers which are not bianisotropic. And there is also a theoretical bound on Willis coupling, and it was derived by Li Kuan in his PRL paper, and he used normalized polarizability tensor. It is the same polarizability tensor as I presented at the first slide on Willis coupling, but if now all the components are normalized by some parameters. And if you normalize the polarizability tensor in that way, you can derive the bound on Willis coupling by conservation of energy, and this off diagonals should stay below 4 over omega squared, and 4 over omega squared is also the bound for Willis coupling. And what is interesting on that slide is if you consider then the case which with maximum Willis coupling, and then you consider the polarizability tensor or with the magnitude components, here you would have in result such a construction with 4 over omega squared for the monopole components and dipole components, and also for the Willis coupling components. And you see that the magnitude is shared, and it is an important feature, and I will also use this feature couple of slides later. Okay,
Anton,
and now
there is a question that in optics you can do such a thing. I guess such a thing would be the scattering that you showed without bianisotropic materials as a purely resonant effect. Is it not the case in acoustics? Same. I think Alexey Shcherbakov, if he would if he can expand his question somehow, may ask something.
I think probably I would, maybe I should say,
I'm sorry,
I'm not
may
quite
I ask?
sure if it is, yes?
Yes, maybe I missed something, but as far as understood, your grating, it adopts propagating minus first order. And in fact, in optics, it is known that you can do such resonant energy propagation to some minus first order. maybe not for the normal incidence, but at least for some conditions, you can have such resonant effect without requirement on bianisotropy on grating material. So my question is this some similar to your effect, or here bianisotropy is an essential condition?
I don't, to be honest, I'm not sure that the bianisotropy is an essential condition. The way how we treated it, it would be an essential condition, but I'm still not, I'm not sure if it is like this, because I said it, but maybe I have really to take my words back. I'm not sure if bianisotropy is an essential condition to provide such effects, but in the case how we designed the things at the later slides, it would be an essential condition.
Okay, thank you.
Okay, then I would go further to that slide. And these are designs from Liquan, which are bianisotropic, or not all of them, but you have a cylinder with an bianisotropic occlusion. And for example, let us take a look at this first example, which is a cylinder with this kind of meander shape channel, and it has a little bit of Willis coupling, but it is quite weak because this is kind of a symmetric structure. It is not symmetric in the inside, but if you consider the scattering of it, it would be almost symmetric. But of course, due to this not perfect symmetry, because of this channel, you see here a little bit Willis coupling. And then you can extend this thing to other designs. If you change this channel at one side to a thinner neck width, you would increase this asymmetry, and of course you would also increase this Willis coupling magnitude. And then if you close the channel at one side, you can achieve Willis coupling magnitudes almost touching or approaching the maximum bound on Willis coupling, which was shown on the slide before. And you can do it in one direction or also in two directions. But now you see that there are already some designs which can maximize Willis coupling and probably also help us to design metagratings with strong properties. But the problem is that you have thermo-viscous losses inside these small channels. And Lee also did another simulations with thermo-viscous losses, and you see the results here. This is again the magnitude of Willis coupling. Here this pink line, and now with the thermo-viscous losses, and it drops from that magnitude to that magnitude when you include the viscous losses. And of course, if you have such a drop, it's not possible anymore to somehow push it and so on again to higher levels. So you can only stay there, and therefore it is important to somehow reduce the thermo-viscous losses inside the metaatoms. And here again, we have also a different study on not just on thermo-viscous losses, but also just on scattering of acoustic metaatoms. And we investigated this kind of acoustic metaatoms with meander shapes, but all of them have been, or they were not bianisotropic. But we have seen in the experiment that for some designs, we were not able to measure the peaks in the monopole and dipole components of the polarizability, which you can see here and here and here and here. And this were also the designs with the thinnest and longest channels. For example, this design number 2 was a special design where you couldn't see anything of this peak. And if you have another designs where you have channels which are a little bit more broad or broader, so you see also here this kind of peaks. And and this is probably could be also probably the issue with the bianisotropic meander-shaped metaatoms, and therefore there is a motivation to find designs which are effective as bianisotropic metaatoms. And For that case, we took again the C shape.
There is a question of how do you introduce losses mathematically?
The losses here have been considered in the simulation. Oh, sorry, not here, not here in that slide.
The question is where do they go in equations?
Where they go in equations?
Yeah, I think that would be the questions in terms of polarizability.
You would usually, if you have the polarizability, we have derived the polarizability for such C shapes, but we have used the differential equation for the Helmholtz resonator for the oscillating mass, and we used for the losses. You can use, for example, the term corresponding to the third derivative or the second derivative or the zeroth derivative, considering the impedance. Maybe I should. Sorry for that. I would just go a couple of slides back, and if you see this equation, this is the impedance model for the simple C shape, and the losses can go to that part, which is the real part of the impedance. But of course, this would be effective losses. We are not considering the real viscous boundary layer. And you also have for scatterer in free space, you have also a component which is not here now, which goes with omega square, which would correspond to radiation losses. And these are the usual losses sources for these acoustic scatterers. Does it help? Okay. Does it answer your question or?
Yeah. I think it did answer Ivan's questions.
Okay, so I would continue. Okay, and here we introduced again the C shape, and the C shape because it is resonant and it avoids thin and long channels. And we made also further improvements on the C shape design. We introduced arbitrary number of apertures, so it's like a multiple C shape design. And this arbitrary number of apertures allow you to control the bianisotropy or Willis coupling. And at the end, it's nothing else as a Helmholtz resonator with multiple apertures. Oh, by the way, here again, there is an equation I have forgotten that I could also show it here. And you see, this is the differential equation for the air displacement of this air mass. And the losses, the lossy part is here for the radiative losses. And in that case, this would be the mass and it would be the stiffness. And we don't have here any viscous losses, but in that equation now, but you could also introduce viscous losses as an additional term corresponding to omega. In that case, it would be omega. In the other differential equation, or in this impedance case, it would be the omega, the part without omega. Because here we considered not the velocity, we considered the displacement of the air mass. And also this differential equation allows in the end a theoretical derivation of polarizability for this simple C-shaped structure. But when you consider cases with strong Willis coupling, of course you want or you would like to have the strongest asymmetry, and it would be again the case with only one aperture, like this simple C shape. And now the question is, can this C shape beat the meander shape in terms of Willis coupling? And to answer this question, we use an experimental setup, which is located in Canberra at UNSW in the lab of David Powell. And as this experimental setup is a two-dimensional waveguide, where you can place some acoustic scatterers inside, and you excite a wave with a loudspeaker on that side, and then you create incident pressure on the scatterer, and you have here a microphone which is moved by a microphone belt on. It can be moved to every position here in these accessible regions, and then you just measure the pressure, and at the end you can use multiple decomposition to get the incident pressure and incident velocity on in the center of the metaatom, and also to get the moment and the moments for the monopole and dipole. And when you know the moments and the incident pressure, it's very easy to calculate the polarizability tensor. You would just use least squares in the matrix form. It is done like this, like here, and you would directly get the polarizability tensor. And here you can also see this setup as a photograph. And here actually you see this metaatom sample. And by the way, this is exactly this sample, because at the beginning of our experiments, we have used this sample to do the measurements. And I think the site is around 2 meters long here. And you see this microphone can here, and this is a microphone belt. And the waveguide consists of 2 plexiglass plates. And here you see also this black wedges, which are made of absorbing foam. Okay, and the next slide, I will show you the polarizability of the C-shaped sample. And that's a normalized polarizability tensor, or components of it. And this part is the monopole component. This part is the dipole component. And this in between, this is parts correspond to Willis coupling. And you see here the experimental results, which are the curves with these error bars. And you see also the results calculated using this equation before this differential equation for the Helmholtz resonator. And you see that they are in agreement. Of course, you have a small shift, and to the higher frequencies here, for example, the difference grows. But there is probably also the reason for the shift, or we probably understood it. I will show it a couple of slides later. And you see also that the Willis coupling magnitude are also in the same order of magnitude like the components for monopole and dipole. And the shape we used was finally made out of steel. And I have mentioned that we used at the beginning this kind of shape, but we recognize that the results were not so good, and we wanted to maximize Willis coupling. And we thought that the problem is probably the impedance of the boundary of this PLA plastics, and therefore we used steel. And we also used steel with high quality surface machining. So the surface was very, very even. Okay, and here at this slide, you see the Willis coupling magnitude for the C shape, and it is normalized to the theoretical bound by conservation of energy. And you see that the experimental results, which are these 2 curves, are in agreement with numerical and analytical data, which are these 2 curves. And the maximum is around 1.75 K times A. And yes, it is not perfect. It is not 100%. And we also have some additional losses here in between the theoretical and a boundary element model. But what could be the reason for it? And such an experiment is not perfectly set up, because you have these plexiglass plates, and they have also some surface impedance with where you introduce additional losses and so on. And we think that this could, because it is very, very complicated to quantify where the energy is gone. But this experimental setup is not perfect, and therefore we think that the energy could dissipate through these plates and go to the foundation of the experimental setup. But there is also another indication for the maximum Willis coupling, and I mentioned previously the shared magnitude. And now you see here the components of the polarizability tensor plotted together with the monopole and dipole components. And this at that region where the maximum is, you see also a magnitude which is almost shared here. Of course, this is experiment, and you see the error bars, which are quite you have here some error, but you can see that the magnitude are here almost shared, and it indicates that we are very close, or we are approaching maximum Willis coupling state.
Anton, the error is due to different measurements, or is it due to the surrounding noise?
The error is due to the positioning of the metaatom, because we used I think something like 12 different angles to obtain the polarizability tensor, and the error depends, of course, how perfectly you align the metaatom, because we did it by hands, and we tried a couple of times to be very, very accurate to get this small error.
Okay, thank you.
Okay, and at that slide, I want to show you the sensitivity of the C-shaped metaatom to thermoviscous losses. And I have mentioned previously that the thermoviscous losses are a big issue for such kind of metaatoms, and here you see results of simulations including thermoviscous losses. And you see these curves, the solid curves for the C-shape, and the dashed curves for the meander shape bianisotropic metaatom. And in case of the C-shape, the drop of the magnitude is only something like 1.02%, which is nothing. But you see here a shift to the lower frequencies. And if you remember the experimental results on the first slide with experimental results, there was also a frequency shift downwards compared to the analytical solution. And we think that it's the reason. If you include the thermoviscous losses, you have such a small shift, and we've seen it also for the meander shape. But in the case of the meander shape, additionally to the shift of the frequency, you see also a drop of the magnitude around 21% for Willis coupling, and therefore you can see that the C-shape is more efficient in the sense of Willis coupling. And another very nice feature is that the Willis coupling of C-shape is broadband. In the case of the meander shape, you have a peak which is very narrow band, and it is not so easy to design, for example, metagrating. If you consider this point here, for example, because the slope is so high, so you would be not very structurally robust. Small change in the wavelengths would change your polarizability drastically. And in the case of the C-shape, if you stay here, yes, you have also a change with wavelengths, but it is still much, much less is for the meander shape structures. And another feature of the C-shape or multiple C-shape is if you introduce multiple apertures, and therefore you can also change the symmetry of your metaatom. And Willis coupling is linked to the symmetry, and therefore if you have the case with only one aperture, you have very strong Willis coupling, and introducing a second aperture would decrease the Willis coupling. And then if you would like to have the peak at the same frequency, you can do the easy approach. You would just change also the size of the aperture at the other side, so you would maintain the frequency and can adjust the peak of Willis coupling to arbitrary number between 0 and a theoretical bound. Okay, it was my last slide on Willis coupling of acoustic scatterers, and now the question is, how can we use such approach to create anomalous reflection. And here I want to thank Yankee Chiang, who have prepared the slides I will show you as next. And this topic is still under work, and it is also considered like an outlook. And I hope you will be then interested afterwards to read the paper, which is already submitted on the topic. Okay. Now, when we have such a metaatom which can give us very strong Willis coupling, we would like to use it to design a reflective metagrating. And of course, we would like to try to stay only with a minus first or plus first direction, and we would place the metaatom in front of a reflective wall. And yes, of course, you have also reflections from the back wall and so on. And at the end, the aim is to adjust the polarizability of single metaatom to neglect the reflection of the backing wall in the zeros direction, and not to have reflection in the plus first direction, and only to have the reflection to the minus first direction, and try to maximize the energy which would be redirected in the direction. And here you see some examples which were calculated using COMSOL. And the examples are all tuned to have a reflection angle of 70 degrees. And the angle of incidence here is 0 degrees. And this is the C-shaped metaatom. And here you have this backing wall, and the reflected wave goes like this. And here is, you see the frequency dependency plot, and you have the maximum of energy linked to the direction at something around 2.43 kilohertz. The same you can also do using higher incident or different incident angles. And now you try to tilt the incident angle in the direction of reflection, sorry, and you have to change a little bit the design, and you can also create the reflection of 70 degrees in that direction with efficiency of 100%. And even if you go to really extreme angles, like 75 degrees of incidence, you can still maintain the angle of 70 degrees of reflection. And here, interestingly, you have even a very broadband effect. So you don't have it only like a peak at some distinct frequency. You have really a region which is not sensitive to the change of frequency. And one further thing I want to show is the exploration of the design space and of the structural stability. And for example, if you consider this C-shape again, and you would try to adjust, or you would change the angle, this angle, alpha, which is the angle in which direction your aperture looks to. And here you have the backing wall again. And for the frequency, you see if you change the angle, of course, you change the efficiency of the plot. The color is the efficiency for the minus first direction, and this is the frequency, and this is the angle alpha. And now, as firstly, we would start at one frequency like 2.4 kilohertz, and then we change the angle. And of course, there is like an optimum angle where you have the best efficiency for this direction. And then if you, for example, change the frequency to another one, you can see that at frequency of 2.6 kilohertz, which is here, you have a quite a broad region of angles where you have still a very high efficiency. And by the way, the incident angle for this example was 30 degrees, and the reflection angle was 65 degrees, which is quite a significant angle of reflection. And you see here that you would it would be not important to place your metaatom exactly at, for example, 120 degrees. It would be also enough to have some tolerances like plus minus 5 degrees, it would be still possible to create such strong reflection, which is a great news because it shows that there is this design is structurally stable. And another thing which is probably also interesting is the incident angle itself, because now you, of course you have placed your metaatom with some accuracy, and now you have an incident wave which is, for example, not perfectly aligned, or even you want to have a device which is capable of treating different frequencies. You want to cover a broadband region of frequencies, for example. And here again, you see the alpha angle, which is the tilt angle of the metaatom, and here in the direction, you see the incident angle. And for example, if you are at the alpha of around 120 degrees, it is possible to achieve a high efficiency for angles between 20 and 40 degrees. Of course, it is not 100%, but even it is not 100%, it is quite reasonable here to have this anomalous reflection at broadband incident angle. Okay, and of course, this kind of structural stability and not sensitivity to the small changes, it creates potential for experiments. So you can try to create such gratings and also measure them because it's not so important to be exactly perfectly accurate at the positioning. Okay, and this is my very last slide, the summary. And I want first I mention again the C-shaped metaatom. If you have recognized, we have used the C-shaped metaatom for all the different designs we have presented today. And the reason for it is that it's very easy to fabricate. It is just a pipe with a slit, or you can use 3D printing or mechanical machining. And this simple geometry allows also for theoretical modeling. And it avoids thin and long channels, which reduces the sensitivity to thermal viscous losses. And I have showed a noise control application using C-shaped metaatoms, and it was possible to design a noise barrier which was sub-wavelengths. It allowed for airflow, and it also is, of course, lightweight because you don't have high masses which you would use for this noise barrier. And I have showed you some slides on Willis coupling, and we demonstrated the experimental Willis coupling of almost theoretical bound, reached 90%, and we did it with a simple C-shaped metaatom. And that, again, it was owing to the reduced thermal viscous losses. And we also showed a simulation how you can tailor the Willis coupling. And in the last part, I have shown some slides on anomalous reflection and shown how it is possible to design extreme reflection angles using this simple C-shaped metaatom. And you have seen that you can get some robust designs using this simple structure. Okay, so this is my very last slide, and I want to thank you for your attention, and I also want to thank all the guys who have participated in the results or on this investigations I have presented today.
Okay, thank you, Anton. That was very interesting. I think, do we have any questions from the audience? I don't see any raised hands yet, but usually they come up in a minute or two. As long as there are none, I have actually a few questions on different topics. So that anomalous reflection that you showed recently, do you understand that it happens in the far field, or is it near field, or is it like independent on the distance from the source?
It is independent of the distance. To design this reflective metagratings, we have used infinite number of cells, and therefore the wave which is created is a plane wave.
Okay, so it's for plane wave. Okay, I'll keep my questions for a bit because we have a questions from Alexey.
Yeah, Anton, thank you very much. I have two small questions. First of all, related to your applications, you said that you can use it for noise control. So what I want to ask, is it really needed for industry to have, let's say, very thin absorbers? Or let's say right now, I mean, like how thin they need it and how thin you can do right now with your approach and in comparison with the commercial one?
Yes, there is actually a need for thin absorbers, because there are a couple of applications where you don't have enough space to have big absorbers. But of course, the ratio of, because you know that porous materials, they are effective above 0.25 times the wavelengths.
Mm-hmm.
And below this frequency, or for frequencies below this borderline case, they are not effective anymore. And in that case, it is interesting to have metamaterials. But the problem is, of course, that the ratio, because the best value we could achieve was 0.15 times the wavelengths. And it is not like a new world, because it's still quite close to this porous materials, of course. Yes, but it is another very, very interesting future, which I didn't mention today, or not showed the results for that. It is air permeability. Mm-hmm. That you allow for airflow, and in that case of this, I will go to that slide. Of this drivetrain, the problem was, for example, that you have to allow for cooling of this drivetrain, because usually you have some efficiency, or you have losses in the electric motor and in the gearbox, and therefore you have, of course, some energy dissipation. And when you use a usual commercial noise capsule, which would be airtight, you would not allow for airflow. And by the way, Jan Pojanka, who are listening also today for the talk, he did the CFD simulations on that kind of application. We did, and he had helped me to check what would be the difference if you have a conventional noise capsule and noise capsule introducing this kind of a metagrating, which would be air permeable. And it is a huge difference, because using the conventional capsule would destroy this kind of gearbox or the motor. Mm-hmm. It would just overheat, and the air metagrating case allow enough fluid flow. Therefore, it would stay below the allowable temperatures. And this is a very important point for many industrial applications, by the way. And if it is possible to go, for example, like in the direction of 0.05 times the wavelengths, it would be also very attractive for industry because of the size of metagratings.
I see. The second small question is the quality of the samples. You said that at certain moment you use this like ABS plastic, or I don't know, 3D printed details, and you said that surface roughness, like it's not enough, and you move to the prototype from steel. So how, like, big influence of surface problems in terms of samples on the quality of metamaterials and acoustics?
It depends really, because if you have designs which introduces, there are many designs already in acoustics which are based on some losses, like designs for example, for some absorption metamaterials which would absorb sound. And in that case, it is probably not so critical to have also surfaces with some losses. But in the case of Willis coupling, for example, when we did this experiment, we recognized that when we have used this sample, which was made of PLA plastics, we were only able to measure Willis coupling at 70% of theoretical bound. And it was like we did some simulations and tried to understand where the losses comes from, and we see that, or we saw that the simulation in the simulation we really reduce Willis coupling when we introduce some real impedance of the surface of the metaatom. And of course, for this case, considering Willis coupling, it was important to have such a high quality surface and also this high quality impedance mismatch between steel and air.
I see. Thank you very much.
Okay, Anton, I had actually, it turns out I had similar questions to Alexey, because when you showed that metaatoms made of plastic, and then showed that the minimum the minimum sub-wavelength size that you were able to achieve was about 0.17 of the wavelength, I thought, well, what does it depend on? Does it depend on the material that you use, or what can be done with that?
Yes, it doesn't depend on the material, depend on the geometry. To be honest, the C shape if you really want to reduce the size of your metagrating and go further in the deep wavelength direction, it could be probably more interesting to change the shape, not to stay with the C shape, but probably to use shapes which would still have a very, very low resonance frequency, because at the end, the problem is you want to have a resonant metaatom which should have the smallest size as possible. And of course, this kind of C shape is very simple, but it is not the most optimal design, considering the low frequency of the resonance and the thickness of it. But of course, if you have here a Helmholtz resonator, it is like the best approach for sub-wavelength resonance to use a Helmholtz resonator. But even here you have further, I think there is still a potential if you want to create metagratings which are more sub-wavelengths to change the geometry and to get better results. But then you have a trade-off with the manufacturing, because the C shape is very easy to manufacture. And if you consider other geometries, for example, some kind of rectangular things, or something, for example, like, I don't know, here you can draw a picture. This kind of design, it is usually not so easy to manufacture, or if you start to introduce some different geometries here inside to increase the movable mass to reduce your resonance frequency, it starts to being more complicated.
Is there any theoretical limit on how low you can go with that, or it just depends on the metaatom?
I think there is no theoretical limit, to be honest, but of course, you would prefer like to have a monopole source which you can excite for noise control, and you would need, it would be necessary to have some kind of like a material there or something like this. And I think there is a limit, but it is probably not a theoretical one, I would think. Maybe if you start to try to find a design, you will find a limit which is like a design limit. But from theoretical point of view, I would think that it is still possible to create some resonators, acoustical resonators, which are very, very small. But of course, they would be not infinitely small. Yeah. They would have some kind of limit. Yes, probably there is you would find it would be possible to find some kind of a limit, but I think it would be like really a design limit that you probably can go small with your thickness of your steel beam or something like that, because you can use resonators which are coupled with elastomechanics. When you will couple the Helmholtz resonator with some elastic things, and due to this elastic properties, you can try to reduce the frequency of the resonator, and of course you can try to use very, very thin elastic membranes, and then you will probably have a problem when you approach layers of the thickness of an atom or something like that.
Okay. And then another thing, is there any codependency of the shape of the, well, not the shape, actually the size of the grating that you have to the bandwidth that it's operational on? Because, and generally, how large can the bandwidth of the either Willis coupling or that noise mitigation be?
Yes, we have seen here in that example, moment here, that the bandwidth of Willis coupling of a C shape and meander shapes is different, but we don't understood the exact reason of it, to be honest, because the Q factor is also, we considered in both cases, if you don't consider the losses, the lossy case, if you consider the red one, which is a case without losses, then the Q factor is the same for the resonator. But but of course you see here a different bandwidth. So we have very, very broadband Willis coupling, and for the C shape, and narrow one for the meander shape. But if you consider the case for noise control, if you remember, there was also a very, very narrow peak of the transmission.
Yes, the peak was pretty narrow as far as I remember.
Yes, and I hope it is not too far. Here, for example, yes, and of course, it's not so perfect, but I think for this impedance mismatch, it's not so easy to increase the bandwidth of this peak. You can, of course, try to reduce the Q factor, and therefore you would have like a smaller peak, but it would seems to be like more broadband. But even if you look here at 10 dBs and consider the area which where you reduce it at 10 dBs, it is already significantly broader as in the case of this high transmission loss. But I think with this approach, with this kind of a impedance mismatch in the resonance approach, it is not so easy to make it more broadband. For this kind of result, probably it would be necessary to have to place more resonators or to use sonic crystals.
Okay, thank you. I think I got it. Do you have any other questions from the attendants? I think there are none. So thank you again, Anton. I think it would be great if you stay here for in the conference for a bit, where you may discuss something, but like after the seminar. So
Okay.
at the moment, I thank you all for coming today, and we'll meet again next Monday, when we'll have the lecture by Konstantin Simovsky about parcel effect, and then we would have a pre-defense of Vyacheslav Ivanov. So thank you all for coming today, and see you next Monday. And if anyone wants to stay to discuss something else with Anton, you're just welcome.